Perfect. Well, hi everyone. It's great to see so many people here. So as Matt introduced me, I'm Leah Bigwood. I'm a PhD student here at the Institute of Astronomy, and I study cosmology. So I study the universe as a whole, kind of its contents, its evolution, how we think it started, and how we think it's going to end up. And what I'm going to do today is take you on a tour of what we do know about the universe. And I'm hopefully going to convince you that we know an alarmingly little amount about what is out there, but that this is exciting because it means that there's a lot to learn and the realm of possibilities are huge. And if anything's unclear throughout the talk, please interrupt me at any point and we can make things make sense. Perfect. Okay, so I think a good place to start is to understand the scales we're talking about when we talk about our universe. So we live in a solar system with the sun at the center and 7 other planets in addition to us orbiting around. Now, if we zoom out a bit further, we live in a galaxy called the Milky Way. And in this galaxy, it contains around 100 billion stars, some of them similar to our sun, some a bit smaller, some a bit bigger, and some of them also have planets orbiting around them. So our sun is just one star out of 100 billion in our galaxy. If we then zoom out even further, we have the universe. And the universe is just everything that could possibly be out there. We think that the universe contains around 200 billion galaxies. So we just live around one star, our sun, in a galaxy with 100 billion stars, in a universe with 200 billion galaxies. And the goal of cosmology is to just understand kind of what is our place in this huge universe, kind of how it started and what's going to happen to us. So I think a good place to start is to think about what are the building blocks of our universe? What's it made up of? So on Earth, we're taught that our whole life that kind of everything is made of atoms. And you think that when you look out into space, you think that everything else would also just be made of atoms. And you think our laws of physics would also work the same out there. The issue is, when we do look out into the night sky, we see some weird phenomena that can't be explained by the usual laws of physics that we use here on Earth and the usual atoms that we know about. So for example, we look out and we see that the universe is not only expanding, but it's getting faster and faster and expanding at an accelerating rate. And this can't be explained by the usual laws of physics that we know about. And astronomers call why this happens. They say that something called dark energy is responsible, essentially. And in order for it to be powerful enough to cause the universe to accelerate so fast, dark energy has to make up around 70% of the total energy in the universe, so an enormous amount. We also know that in order for galaxies to form in the way we see they do, and for them to be so many of them out there, there must be some sort of invisible matter, some matter that we can't see is there, but we know should be there. And essentially what we could do is we call this dark matter, and I'll go onto this a bit more in a bit. But essentially there's all of this invisible matter also out there, and that has to make up around 25% of the total mass in the universe. So we've said we have dark energy, dark matter, making up around 95% of the universe. And ordinary atoms that we know about make up only 5%. And when astronomers call something dark, like dark energy or dark matter, it essentially just means we know it should be there, but we have no idea what it is, basically. So how do we get to this point where essentially 95% of the universe, we don't know what it is, and we have these very sci-fi terms like dark energy and dark matter? How do we get to this point where we know these things should be there? So that's what I'm going to be talking about today. Okay, so let's start with dark matter. How do we know it's there in the first place, and what could it be? So in our solar system, we have our sun at the center, and we have Earth orbiting around it. And the sun is very heavy and exerts a very strong gravitational force. And as a result, the Earth feels that gravity and orbits around it in roughly a circle. And if we wanted to work out how heavy the sun was, we could use the laws of physics, the laws of gravity, to kind of understand and figure out how heavy the sun is based on how fast the Earth is moving. And we can use this equation that I have shown here on the screen. So we can say that the mass of the sun is equal to, the mass of the sun, m, is equal to the speed the Earth is moving around the sun, which is that v squared there. R is the distance between the Earth and the sun. And then g is just the gravitational constant. It's essentially a number that's the same everywhere in the universe and essentially just tells you how strong gravity is. So we can check that this equation works. We can plug in numbers. So we know that the speed the Earth is moving around the sun is around 30,000 meters per second. We know the distance between the Earth and the sun is around 1.5 times 10 to the 11 meters. And we have this big number for the gravitational constant that's just always there. So when we plug in these numbers, we get that the sun should weigh around 2 times 10 to the 30 kilograms. So 2 and then with 30 zeros. And we can use other methods to test this and other methods to try and weigh how much the sun is. And we get around the same answer. So we know this method should work well, and we see that it does. It gives us a very heavy value for the sun, as we'd expect. So what about if we look on a bit of a bigger scale? How would we then weigh a galaxy? Well, we can use a similar idea that galaxies are also extremely heavy, and they exert a very strong gravitational force. And we said that galaxies can contain around 100 billion stars, and these stars are also going to orbit around the center of the galaxy, like the Earth orbits around the sun. So what we can do is we can use the speed that stars are moving around the center of the galaxy to also weigh the galaxy. So if we plug these numbers in, if we plug in the speed of the stars are moving, we get that a galaxy should weigh around 1 trillion suns. So 1 trillion suns is kind of what the stars feel is there. It's the matter that we calculate when we use the laws of gravity. The issue is, if we actually look up and look at a galaxy and try and observe it, we only see around 0.2 trillion suns. So to emphasize, we're about 800 billion suns off. And we call dark matter the difference between the number that we weigh the galaxy when we use the laws of gravity and the matter that we actually see is there when we kind of add up everything. So what is all of this invisible matter? We know that it should weigh this amount, but we don't see it, and we're 800 billion suns off. So there are two possibilities. So firstly, maybe just the equation we used is wrong. The issue is this equation has worked time and time again. We rely on it when we have satellites orbiting the Earth. We rely on it when we send rockets up to space. And the planets move around the sun according to this equation, basically, like clockwork. And scientists have tried to come up with a better theory of gravity, but it's never as good as the kind of ones, like the equations we have here. So the only alternative is that there must be something invisible there, making up all of this extra mass in galaxies. And our best bet is that we think it's some sort of particle, and we think it's something called cold dark matter. And what this means is it's some sort of particle that we know must be very heavy, and cold just means it moves quite slowly, as in it can't get to very high speeds, because otherwise if it could get to high speeds, it would then kind of escape from the galaxy and it wouldn't be held there, we wouldn't have all of this extra mass. So this is where we're at the moment, and we've tried to detect this particle kind of using particle accelerators and things like this, but so far we haven't found anything. And you can imagine it's very difficult in the first place because we know it is invisible. Okay, so we said that dark matter is all of this kind of extra mass in galaxies that we can't see. But what about dark energy? We said this is what's responsible for the universe to be accelerating. But how do we know the universe is accelerating in the first place? So the best place to start is thinking about the laws of gravity. And in 1917, Einstein was developing these laws, which we call general relativity. And he wanted the universe to be static and eternal. He essentially wanted it to be a kind of fixed box that had existed forever. It wasn't expanding or contracting. And when he was writing his equations, he realized that all of the galaxies in the universe would exert a lot of gravity, and they'd kind of pull the universe in and cause it to start contracting. As a result, he had to introduce something else into his equations to kind of counterbalance the gravity and keep the universe as this fixed box. This something he introduced was called the cosmological constant, and it's represented by this lambda symbol here. And it was just an extra term he threw in to keep the universe as a box. Now, around 10 years later, Hubble wanted to test whether the universe truly was a static box. And he used the biggest telescope available at the time to measure the distances to galaxies and the speeds of them. Because if he saw that they were moving away from us, then the universe was probably expanding. And if they were moving towards us, the universe was probably contracting. Now, in order to measure these speeds, he used a very clever technique that we call redshift. So if you have a galaxy far away from us in the universe, the light travels to us as a wave. Now, if the universe is expanding and the galaxy is moving far away from us, then this light is going to get stretched out on its way to us by the universe expanding. And if the galaxy is moving away faster, this wave is just going to get stretched out even more. Now, we call this redshift because in the visible spectrum, so like the colors we see day to day, red light has a longer wavelength that looks more stretched out than blue light. So essentially, if a galaxy is moving away from us at a speed, its light gets stretched out, and then the light looks more red to us. So what Hubble found was that the more distant a galaxy is from us, the more its light has been redshifted. So what that means is that the further a galaxy is from us, the faster it appears to be moving away from us and receding into space. This led to the alarming conclusion that the universe isn't a fixed box after all, but that it's expanding. So as we remember, Einstein put this cosmological constant into his equations in order to keep it a fixed box. But when he found out the universe was expanding, he realized he'd made a big mistake by putting this factor into his equations. And as a result, he removed it and he called it his greatest blunder. And for around 70 more years, it was widely accepted that, yes, the universe was expanding, but eventually the gravitational pull from galaxies would kind of exert this gravity and cause the universe to slow down, and maybe eventually stop. Astronomers, however, weren't just satisfied with that answer, and they wanted to go out and measure the expansion rate of the universe. But that wasn't possible for a very long time because you needed very good telescopes that could look very far into the universe. And it was only near the year 2000 where it became possible. And in order to do this, they had to use a very clever tool called standard candles. Now we know if we have a candle, it has a fixed brightness, and if we move it far away from us, it's going to look fainter, and if we move it further away from us, it's going to look even fainter. So we can use the brightness that we see to figure out how far away it is. And we can use a similar thing in the universe. So we can say that we have these objects called type 1a supernovae, and essentially they're a star like our sun, but a bit more compact. And at the end of their life, they explode, and they explode in an explosion with a constant brightness always. So if we see one of these supernovae exploding and they look quite faint, we know it's far away from us, and if it looks bright, we know it's close by. And we can use this to build up a distance scale in the universe. So in around the year 1998, two independent teams were working on this, and they were looking at measuring the brightness of supernovae. And what they found was that even knowing the universe was expanding, these supernovae were coming out much fainter than we expected them to be. So they must be even further away than we thought. So this meant that the universe was not just expanding, but it must be expanding way faster than we thought it could be. And they learned that essentially the universe's expansion is accelerating. This led to the Nobel Prize in Physics in 2011. Okay, so what does this mean for our picture of the universe? So we have the Big Bang that kind of set off the expansion of the universe. But at this point, the universe was still quite small. We had all of this matter still kind of quite densely packed, and exerted a very strong gravitational force. As a result, it caused the universe's expansion to kind of slow down a bit. But then suddenly, around 5 billion years ago, something kicked in, and the universe's expansion suddenly started accelerating. And we essentially have no idea why the universe expansion suddenly started accelerating so fast. But we call what's responsible for this sudden acceleration dark energy. So what could dark energy be? So in order to answer this, we go back to Einstein's theory of the cosmological constant. We said that he put it into his equations to keep the universe a fixed box, but then he removed it when he learned the universe was expanding. But it seems like he might have actually been onto something. So Einstein's cosmological constant says that empty space can possess its own energy. Essentially, even if there's nothing there, no atoms, space itself still has its own energy. And this energy can cause space to expand and kind of push the universe out. So if the universe is expanding, we're getting more space and therefore more dark energy, and then the dark energy is causing the universe to then expand even further. So essentially we get a kind of exponential reaction where we're having more space popping up, more dark energy, and the universe starts expanding faster and faster and at an accelerating rate like we observe. And when you run these calculations, you find out that this cosmological constant is quite a good fit to kind of what we see in the universe. Okay, so let's summarize what we do know about the universe. So we've said that we think we have this dark energy in the form of Einstein's cosmological constant. And we also think that we have these invisible particles that we call cold dark matter. But what does this mean for us? So in this theory, the universe is nearly 14 billion years old. And our fate is that as the universe kind of keeps expanding at an accelerating rate, eventually galaxies are going to move away from us so fast that the night sky is essentially going to look completely blank because the galaxies have all moved away. And then eventually, which I caveat will be in billions of years, so nothing to worry about, all of the structures in the universe are going to separate into their individual particles. Everything will be completely infinitely far apart, and the universe will cool to the coldest possible temperature, which we call absolute zero, and we'll have a fate called the Big Freeze. Now, obviously, this isn't a very nice thought. Could happen to us. So it'd be nice to think that maybe this theory could be wrong. Maybe we might have some much nicer fate. And there are hints that this might be the case. So one of these is something called the H-naught tension. So H-naught is just the number we put on how fast the universe is expanding. It's just the expansion rate of the universe. And we could say, and we remember that we can measure how fast the universe is expanding using these type 1a supernovae. But there's another method we can use, which is using the light from the Big Bang. So essentially, when we had the Big Bang, we suddenly had all of this light and radiation kind of springing into place. And this light has been traveling around the universe for 14 billion years, and we can measure it now, today, around us, completely surrounding us. And it's called the cosmic microwave background, because this light was very high energy when it first was created by the Big Bang. But as it's traveled to us, its wavelength has got longer and longer, and now it has the same wavelength as microwaves. So essentially, we can use this light also to measure the expansion rate of the universe. So there are two kind of tests we can do. We can either use these supernovae, or we could use this light from the Big Bang, but they should give us the same answer, because they're measuring the same thing, just how fast the universe is expanding. So in this graph here, I show the different values that the two teams are measuring for the expansion rate of the universe. I show the supernova team in blue, and in black I show the team who use the cosmic microwave background. And on the left of the plot here, you can see that the two measurements are in quite good agreement, and their error bars are kind of overlapping quite well. But as time goes on and our measurements have got better and better, these error bars have got smaller, and we found that the measurements no longer agree with each other. The supernova team are getting a measurement of around 75, and the people who use the light from the Big Bang are getting a value of around 68. But these measurements should agree. They're literally measuring the exact same thing. So what could be the reason for this? Well, your first guess would be that, well, maybe there's an issue with one or both of the measurements. Maybe one of their telescopes wasn't calibrated correctly, or maybe there's something else astrophysical that they're not accounting for. And maybe this could be the case, and then this would be helpful, because then we can correct one of the measurements, we know how fast the universe is expanding, and we can go on with our quite nice theory of dark energy and dark matter that do seem to explain the universe and what we see quite well. The other alternative is that maybe our measurements are right and our theory is wrong. Maybe dark energy isn't the cosmological constant using Einstein's idea, or maybe we don't really understand how gravity works. Either way, there's a huge realm of possibilities, all with very different fates for the end of the universe. And it's really exciting to try and explore these and see if we could get a better answer. And just as a little addition, this is what I work on. So here I show one of the computational simulations that we run, and it's been the background of this talk the whole time. And essentially what we do is we start the universe off right at the beginning on our computer, and we look at slightly tweaking the physics. And then we evolve the universe kind of to the present day, letting galaxies and stars and everything else form. And then we look at what we get out, and we can compare it to what we actually see out there. And you can see we get these very pretty simulation pictures where we see all of the structure in the universe, and we call it the cosmic web. So it's a really fun game, kind of having your own little universe on your computer and kind of being able to tweak the physics how you want. Okay, so to summarize, we've said that in order to explain what we see in the universe, it expanding so fast, and also all of this invisible matter, there must be something else that's not atoms and not our usual laws of physics. And this is what we call dark energy and dark matter. And these make up such a huge portion of what we know makes up the universe, but we don't really know what they are. We have some rough idea, but we've never really directly detected them. But there is some hint that this theory might be wrong of dark energy and dark matter because of these tensions we see between the measurements, like the H-naught tension. And in that case, maybe there's new physics, maybe we do need to completely rethink things, and we might have a completely different fate of the universe than we initially thought. Okay, thank you very much, and please let me know if you have any questions. Perfect. I think Matthew's coming back.
Any questions for our speaker?
Hi. So it depends kind of what size you're working with. So I'm working with a simulation at the moment that has a box size that's 100 megaparsec. So that's like 3 times 10 to I think the 26 meters a length. And these take around like 3 months to run and use an incredible amount of computational resources that honestly is not very good for the environment, and we're working on offsetting this. But yeah, they take a very, very long time.
I'm so impressed you have the number of meters in a megaparsec.
Yeah. Hiya.
Are you sure that the Big Bang was actually the Big Bang, and it's not, and it's actually just it could have been a different way the universe was created. So it could be dark energy, but in another different way.
You've really cracked it. Honestly, there are yeah. Honestly, you should know the amount of papers that come out every week that claim exactly that. They say that dark energy might have been what started the universe as well, and that maybe it just turned off for a bit and then turned back on. But yeah, we don't know. All we know is that something suddenly caused the universe to start expanding. But yeah, I mean, you're very right. Cool.
Any more questions? Yes.
Question.
Yeah.
You started by saying you study the universe as a whole. Do we actually know the boundaries of the universe? And I guess it relates to the modeling question.
Mm-hmm. So I guess when I talk about the universe, I mean the observable universe. So any light that could ever potentially reach us. That's what we have to define as the boundaries, because obviously there could be infinitely more things beyond that. We could have some sort of multiverse and other little pockets and things of universe popping up, but all we generally just define it as the observable universe.
Any more? Oh, sorry, I didn't see you over there. I'm sorry.
Yeah, I'll be honest, I'm still slightly confused because we have this dark energy which is pushing things out, but you're also arguing that that fits with Einstein's theory of a fixed. Are you arguing that actually the universe still could be fixed in terms of stuff, but what happens is the dark energy just pushes it and stretches it?
So what we're arguing is that Einstein put this into his equations in order to keep it fixed, but we're just kind of using it as a tool, essentially. We're saying it's not exactly in the way that Einstein used it. It's probably more powerful than he intended it to be, and it essentially then overpowers the gravity and causes the universe to push out more than he initially intended it to. Because he used it just to keep the universe fixed and exactly counterbalance gravity, but we're saying it's now more powerful than gravity.
How did he see dark energy as keeping the universe fixed?
So he saw it as something that created a kind of outward pressure that kept the universe exactly in balance with the gravity. Cool, thank you. Hiya.
I'm fascinated how you see your simulation, because obviously computers don't naturally do that. So if you start with a Big Bang, then it will just be uniform. So do you use observations of the background radiation, or?
Yeah, you're bang on. Yeah, exactly. So we can't start it exactly at the Big Bang. We have to start it a bit later. And essentially we take a kind of random field of density fluctuations and then evolve them. Because as you say, if it was just a uniform, you wouldn't get anything coming out. So you have some fluctuations that then kind of accrete more matter, and then you get galaxies forming and stars. But you can't start from zero.
Would that mean your X months of simulation is kind of dependent on that initial seed being sensible?
Yeah, exactly. And we run different initial seeds to kind of see, because if you have kind of one fluctuation, you might suddenly get a huge galaxy that you wouldn't expect to see. So you have to run different ones to see what you get out, because we don't know what the initial conditions of the universe actually were.
Right. Do you have any more pictures of your simulation?
I actually could get some up. 1 second. Do you know how to do this? How I would show? Show an overleaf.
Yeah, so if there's a virtual monitor here, so if you bring something up and then you drag it to the right,
Okay.
it will go over there.
This is nice for me. It makes me feel like my work is worth it. I've created all day making pretty images, so it's perfect timing.
Is this, sorry, I missed it. Is this all illustrious?
This is Fable,
Cool.
but running it in a huge box.
Yeah. Oh, cool.
Let's see where my... It's taking a long time to load because it's a very heavy image. Okay, how would I then
So
do
if you
this?
just take this window, and then if you
You go ahead.
just drag, if I can just drag this.
Maybe if you drag the tab, would that work?
Actually, I'll tell you what, if you, there we go, so this should appear here.
Oh, cool.
And then, like so. Oh, and then you have to do the overleaf magic. Oh, I messed up your overleaf. I'm
That's
sorry.
okay, don't worry. How do I see my mouse?
Um,
Can I use this one?
oh, no, sorry, I was just saying to use this screen.
Okay.
How do you see the mouse?
Sorry.
So yeah, there it is.
Okay, so could you click back on? Oh wait, don't worry. It's just got a big delay, so there we go. And then we can finally reveal some nice images. Okay, and then if I zoom in, is that the plus?
Yeah.
Yep. So this is one of the other images we've been working on. So what I've shown here is the kind of entire density field of our mini universe that we're running. But it's not that mini, it's actually took a very long time. And then I show what happens if you zoom into one little region, and then if you zoom in even more and look at kind of the temperature fluctuations and things like this.
So how old would this universe be?
So this would be the universe at the present day. And
So why are we not seeing just stars and planets?
so this is kind of so zoomed out that you're looking at kind of how galaxies are all joining up. Yeah, it's literally just density. So there are millions and millions of galaxies kind of along this web that we see. Wait, hi.
Okay, so let's do two more questions, then we'll have a tea and biscuit break.
How close is that to what you actually observe?
Pretty close, actually. So this is our run where we just use the normal physics that we know work in the universe. So you'd hope we wouldn't be too far off. And like our usual laws of dark energy and these things. And when you look at how many stars you have, how many galaxies, it's matching up pretty well at the moment.
Oh, so many hands.
I can chat to more people afterwards.
Okay, let's do a couple more that came up first, and then are you happy to stay around?
Yeah, of course.
Answer any more questions? Okay, so let's go right to the back.
I looked up the multiverse.
Mm-hmm.
Is that something that Marvel has picked up from science, or is it the other way around?
So, I mean, I think it's something Marvel's picked up from science. It's something that's very possible, but it's just because it's not observable to us, we can't really treat it as science. Because essentially what would have happened was, in the very early universe, a very small packet of it, we think, suddenly expanded into our universe. But then it's also very possible that another little packet also started expanding very fast, and that would be a multiverse. But we can never really get to that. People think all the time that they've kind of found signatures of a multiverse, essentially like hints that two bubbles are kind of against each other. But yeah, it's definitely, could be a possibility. It's not completely science fiction.
Okay, did you have a question as well?
I was wondering, why is it that of all the particles we've discovered so far, even in particle accelerators, why are none of them a viable candidate for dark matter?
So that's a very good question. Firstly, most of the ones we see do interact with light, so we know that we can see them, so they're not invisible and work as dark matter. And also they just don't have the correct kind of masses that we need for it to be dark matter, and kind of some of the other properties that would make galaxies form in the way we see they do.
Wonderful. Okay, so we're going to have a tea and biscuit break and then be back in here for a planetarium show. Can we thank our speaker again?
Thank you.